There is nothing else in the universe quite like a neutron star. It is not a planet, and it is not an ordinary star. It is the collapsed core of a massive star that has reached the final stage before becoming a black hole. Imagine more mass than the sun squeezed into a sphere only about 20 kilometers across. It can spin hundreds of times every second, and its magnetic field is powerful enough to alter matter itself. Welcome to Beyond the Cosmos. If you enjoy exploring the most extreme places in the universe, subscribe and join us for more. A neutron star begins with the death of a massive star. When a star between about 8 and 20 times the mass of the sun runs out of nuclear fuel, the outward pressure that has held gravity back for millions of years disappears. Gravity takes over almost instantly. The core collapses in less than a second. As the outer layers rush inward, they slam into the compressed core and rebound in an enormous shockwave. That shockwave tears the star apart in a supernova. For a brief time, a single supernova can outshine an entire galaxy. It releases more energy in a few seconds than the sun will produce during its entire lifetime of roughly 10 billion years. The explosion leaves behind a surviving core. If it is massive enough, it collapses into a black hole. If not, it becomes a neutron star. The numbers are almost impossible to picture. A typical neutron star has between 1.4 and about 2 times the mass of the sun, yet it is only around 20 kilometers wide. Its density is roughly 100 trillion times greater than water. A single teaspoon of neutron star material would weigh about 10 million tons on Earth. Its gravity is equally astonishing. Surface gravity is around 200 billion times stronger than Earth's. No human could survive there. You would be compressed into a layer thinner than an atom almost instantly. The inside of a neutron star remains one of astronomy's greatest mysteries. The pressure forces protons and electrons together to form neutrons packed so tightly that ordinary matter can no longer exist. Some physicists believe the center may contain exotic forms of matter, including quark matter, but no one knows for certain. Every clue comes from observing neutron stars across enormous distances. These stellar remnants are also extraordinary spinning machines. As the original star collapses, its rotation speeds up because angular momentum must be conserved. The same principle allows a spinning figure skater to rotate faster by pulling in their arms. Some neutron stars rotate hundreds of times each second. The fastest known pulsar, PSRJ 1748-2446 AD, spins 716 times every second. Its equator moves at nearly 1/4 of the speed of light. These rapidly spinning neutron stars are called pulsars. Powerful beams of electromagnetic radiation stream from their magnetic poles. If one of those beams crosses Earth, astronomers detect a pulse with every rotation. The timing is remarkably consistent. When Jocelyn Bell Burnell discovered the first pulsar in 1967, the signal seemed so regular that researchers briefly labeled it LGM1, short for Little Green Men. They quickly realized the source was natural, but the discovery transformed astronomy. Today, pulsars help scientists test Einstein's theory of general relativity, detect gravitational waves, and measure the structure of our galaxy with incredible precision. Some neutron stars are even more extreme. These are magnetars. An ordinary neutron star already has a magnetic field about 1 trillion times stronger than Earth's. A magnetar is roughly 1,000 times stronger still. It has the most intense magnetic field known in the universe. Fields this powerful change the behavior of matter. Atoms become distorted, and electrons no longer behave the way they do under normal conditions. If a magnetar replaced the moon, its magnetic field would be strong enough to erase the magnetic strips on every credit card on Earth. Closer than that, the radiation and magnetic forces would be deadly. Magnetars also experience violent fractures in their crust. These events are called starquakes. They release enormous bursts of gamma rays. In December 2004, the magnetar SGR 1806-20 produced a flare that released more energy in 1/10 of a second than the sun produces in about 250,000 years. Even from roughly 50,000 light-years away, the burst affected Earth's upper atmosphere. Only about 30 confirmed magnetars are known, making them among the rarest objects in the universe. Some neutron stars orbit each other in binary systems. As the stars move closer together, they orbit faster. The faster they orbit, the more energy they lose. Eventually, they collide. In 2017, the LIGO and Virgo observatories detected gravitational waves from two neutron stars merging about 130 million light-years away. Telescopes around the world also observed the event, making it the first confirmed example of multi-messenger astronomy. The collision created a brilliant explosion known as a kilonova. It also confirmed a long-standing prediction. Many of the universe's heaviest elements are created during these collisions. Gold, platinum, and uranium cannot be produced in large amounts inside ordinary stars. They form when neutron stars merge and scatter their material across space. The gold in jewelry, the platinum used in electronics, and much of the uranium found on Earth were likely created billions of years ago in neutron star collisions before becoming part of the cloud that formed our solar system. Neutron stars cannot exist forever. If one gains too much mass from a companion star, or if two neutron stars merge into an object that exceeds the Tolman-Oppenheimer-Volkoff limit, neutron pressure can no longer resist gravity. At that point, collapse is unavoidable. The neutron star becomes a black hole. It is the last stable state matter can reach before gravity completely takes over. Everything we have explored, the crushing density, incredible spin, immense magnetic fields, pulsars, magnetars, gravitational waves, and the creation of heavy elements, exists within the narrow boundary between a supernova and a black hole. Neutron stars show us what happens when nature pushes matter as far as it can go, without crossing that final line. If you enjoyed this journey into one of the universe's most extraordinary objects, subscribe to Beyond the Cosmos so you do not miss the next episode. Leave a comment and tell us which neutron star fact surprised you the most. There are still stranger places waiting beyond the stars.